Hi, good afternoon. This is David Gramaje. I am plant pathologist, and in this seminar I will talk about grapevine trunk diseases with a special focus on disease management. Grapevine trunk diseases, GTD, are caused by a group of fungi that primarily infect grapes through pruning wounds, subsequently colonizing the vascular tissues. Symptoms of what we today call GTD, as well as fungi associated with them, are not known. The disease, currently known as Esca, may be as old as vine cultivation. However, the first formal record of a GTD dates back to the end of the 19th century in France, where Esca foliar symptoms were first described and named feuilletage and apoplexy, and thought to be caused by the basidiomycetes Stereomyrsutum and Felinus ignarius. Although GTD have been known since the end of the 19th century, their significance and impact on plant health have only been recognized recently. The recent increase of GTD incidence worldwide is believed to be the consequence of several factors. Firstly, the grapevine planting boom experienced worldwide during the 90s, which not only increased the movement of potentially contaminated propagation material, but has led to the increased area of vineyards around the world reaching an age where symptoms are expressed and therefore becoming more visually prevalent. Secondly, drastic changes in production methods that have rarely favored fungal infection, such as the transformation from the traditionally low-density head training to more high-density spur-prune trellis vineyards, often mechanically pruned. Finally, in some countries, the phasing out of the sodium arsenite, benzimidazole fungicides, and methyl bromide in the early 20th century, due to environmental and public health concerns, eliminated the most effective chemical products available against GTD fungi. Accordingly, it is well accepted that GTD represents one of the major threats to the future economic sustainability of viticulture, causing significant economic losses due to the reduced yields, increased crop management costs for cultural and chemical preventive measures, and shortened lifespan of vineyards. This pathosystem is very complex due to the different reasons. To date, up to 135 fungal species belonging to 35 genera have been associated with GTD worldwide, although Koch's postulates have not been completed for all of them. However, GTD fungi account for the largest group of pathogens known to infect grapes. Petri disease and blackfoot affect young grapevines, whilst the diseases Eutypa, Botryosphaeria, and Phaeomoniella diebac and Esca affect mature grapevines. Botryosphaeria and Phaeomoniella diebac can also affect planting material and young vines. Blackfoot is recognized by black, sunken, necrotic lesions on roots and a dark or reddish-brown discoloration in the base of the trunk of affected vines. Bark removal reveals black discoloration and necrosis of wood tissue which develops from the base of the rootstock, causing death of young vines. Up to 32 species in the genera Campylocarbon, Cylindrocladiella, Dactylonectria, Ilionectria, Neonectria, Pleiocarpon, and Celonectria have been reported to cause blackfoot disease, being the most prevalent ones Dactylonectria torresensis, Dactylonectria macroderima, and Ilionectria liriodendri. Petri disease can be recognized by the presence of dark caloric phenolic compounds in silent vessels of the trunks, which exudate out of the vessels when cut in cross sections and dark streaks in longitudinal section. The fungal species associated with Petri disease include Phaeomoniella chlamydospora, 29 species of Phaeoacremonium, Pleurostoma richardse, and 6 species of Cadophora. Foliar symptoms associated with both diseases include overall stunting, delayed bud break, shortened internodes, chlorotic foliage with necrotic margins, and wilting of leaves or the entire shoots. However, these symptoms not only overlap, but they resemble symptomatology associated with abiotic disorders such as winter damage, spring frost, water stress, and/or nutrient deficiency. In mature vines, two forms of the Esca disease, chronic and apoplectic, have been traditionally reported to occur in vineyards. In the chronic or mild form, the most characteristic foliar symptom corresponds to the tiger stripe pattern. Leaves display multiple banding discoloration surrounding dry, light or red-brown necrotic tissue on the leaf blade, often bordered by narrow red or yellow blotches. The acute or apoplectic form is characterized by a sudden wilting of the entire plant or of one arm or several shoots. Cross-sections of Esca-affected trunks reveal a variety of internal bud symptoms, such as black spots in the xylem, eventually surrounded by pink to brown bud discoloration, brown to black vascular streaking, and in older vines the bud may develop a white to yellow soft rot. The etiology of Esca disease has been a matter of discussion among scientists over the last 20 to 25 years. The main hypothesis is that young vines infected with the pioneer fungi Phaeomoniella or several species of Phaeoacremonium, the most prevalent Phaeoacremonium minimum, can later develop Esca symptoms following further colonization by several Basidiomycetes species. The main bud symptoms of Eutypa, Botryosphaeria and Phaeomopsis diebac is wedge-shaped perennial cankers, indistinguishable among diseases, and circular to non-uniform central staining of the bud observed in cross-sections of affected bud. Foliar symptoms of Eutypa diebac include stunted shoots with chlorotic leaves that are often cupped and with necrotic margins. Eutypa diebac is caused by 24 species in the Diatripaceae family, the most virulent and common of which is Eutypa lata, and is the only species known to be responsible for the foliar symptoms. Botryosphaeria diebac often presents a lack of spring growth from affected spurs with shoot diebac. To date, 26 species within the family Botryosphaeriaceae have been associated with Botryosphaeria diebac of Grapevine, Neophysicoccum parvum and Diplodia seriata being the most prevalent species in Europe. Presently, 18 species in the genus Diaporte have been shown to be pathogenic on grapevine bud. Among them, Phaeomopsis diebac is primarily caused by the most virulent Diaporte ampelina, which has long been known as the causal agent of the grapevine disease named Phaeomopsis cane and leaf spot in US or scoriose in Europe. The second reason explaining the complexity of this pathosystem is that fungi associated with GTD have different biology and epidemiology. Some are commonly found in soil and infect the plant through the roots and the base of the rootstock. Others can be propagated through the use of infected cuttings, and most of them are primarily spread through the dispersion of airborne spores and penetrate into the plant through the pruning wounds. And the third reason, no curative measures are known to control GTD. They would be best managed by an integrated disease management strategy that combines the use of preventative measures, control options through all steps of the production process. And these preventive measures can be applied in nursery, model blocks, in the preparation processes, nursery field, and in newly established and mature vineyards. In this presentation, I am going to discuss the currently available strategies to reduce GTD infections based on published research giving priority to experiments performed under nursery and field conditions. Products and the strategies to protect pruning wounds in model blocks are the same as those applied to mature commercial vineyards. Therefore, this issue will be addressed later at the end of this presentation. Proper pruning practice and protection, as well as cultural practices and sanitation, must be applied in model blocks. Rootstock model plants can be cultivated in several systems: sprawl on the soil surface, sprawl on woven fabric, and with horizontal or vertical trellis system. Vines on a trellis system have some agronomical advantages, and it can also eliminate or reduce potential soil surface pathogen contamination. In contrast, this system is much more labor-intensive and expensive than vines sprawl on the ground. Different systems can be used to irrigate nursery mother blocks. Drip irrigation is strongly recommended since overwatering favors most soil-borne pathogenic fungi and reduces aeration, and overhead sprinkler irrigation can trigger spore release of Botryosphaeria, Phaeoacremonium, and the Eutypa species. Removing and destroying all diseased wood from the vineyard still remains the best practice to reduce the number of new infections for all GTD pathogens affecting mother blocks and mature plants. If we have a look at, for example, the disease cycle of Botryosphaeria diabag, from the dead wood present in the plant as well as the pruning debris, pathogens can produce fruiting bodies. From those structures, spores are released under favorable climatic conditions. These spores penetrate into the plant through the pruning wounds, colonize the vascular system, and cause wood cankers. So the best way to stop this disease cycle will be to remove the dead wood or the pruning debris at this moment. Infected wood and pruning debris can be destroyed by burning, mulching, and incorporation into the soil of the vineyard or composting. Burning has several environmental disadvantages, therefore this practice is being replaced by other options such as composting or mulching. In France, researchers showed composting of vine material along with sheep manure and garden residues for 6 months to successfully eliminate inoculum of GTD pathogens from grapevine wood tissue. Just to finish this section of nursery mother blocks, I recommend this paper where we establish a protocol for the management of grapevine rootstock mother vines to reduce latent infections by GTD pathogens in cuttings. We gave some recommendations regarding the establishment of mother blocks, renewal of mother vine trunk every 5 to 10 year intervals, removal of the entire mother block every 15 years, and make all pruning cuts to retain long internodes and improve the continuity of sap flow. This aspect will be addressed later in my presentation. In the propagation processes, priority should be given to the application of biological and physical treatments due to the reduction in the availability of efficient chemicals in nurseries and the search for disease-tolerant planting material. 3 important things to consider in this section. Nurseries provide nearly optimal environments for fungal development, wet and humid conditions in hydration tanks and calusing, high root density within calusing containers and field rooting stages, close spacing of plants, so this will enhance opportunities for pathogen spread and reproduction. Even with these favorable conditions for disease development risk, disease will not develop if the pathogens are not present. However, production practices in most nurseries provide many opportunities for fungal trunk pathogens introduction through poor sanitation practices or through pruning wounds, the disbudding stage, or the dramatic action of putting together the scion and the rootstock in an omega grafting machine. Unfortunately, it is often difficult to detect trunk disease-infected plants in the nursery. It is frequent to see in field nurseries this type of high-quality planting material with no physical defects, no foliar symptoms, graft union healthy and strong, appropriate length and thickness of the rootstock with at least 3 to 4 buds, and probably with healthy and evenly distributed roots. However, when we cut these plants at the base of the rootstock, we always appreciate this necrosis from which we frequently isolate fungal trunk pathogens. It's very common to see external asymptomatic plants. These fungi can act as latent pathogens and may become pathogenic to the grapevine following biotic and abiotic stress factors. Up to date, it is not possible to ensure that propagation material is free of GTD pathogens by non-destructive sampling. Given this scenario, the message is clear: start clean, keep it clean. The recommendations are related to the use of pathogen-free plant material, clean grafting machines frequently, maintain a high standard of general cleanliness in the nursery, particularly the grafting, calusing and cold rooms, never reuse calusing media, which is a potential source of GTD inoculum, and avoid soaking cuttings in water for long periods of time. This study represents the ideal situation for an integrated management program against GTD in nurseries. In this experiment, the researchers evaluated several treatments at different steps of the propagation process and concluded that these two strategies, application of hot water treatment to grafted vines after uprooting and before selling them to the grower, and application of Benovil or carbendazim before cold storage, spore kill before grafting, and Tricoflow, a product containing several strains of Trichoderma atroviridae, after grafting and before planting, were the most efficient to reduce GTD infection in South African nurseries. However, although chemical control was effective in the past to control GTD pathogens in nurseries, only kinosol is currently authorized in Europe, in particular in Germany, against these fungi, and its efficacy is very low compared to, for example, carbendazim, ciprodenil, or fludeoxinil. One of the possible alternatives to chemical control is the application of biological control agents. Recently, researchers in Italy and Spain demonstrated that the application of Trichoderma atroviridae strain SC1 at the hydration stage effectively reduced infection by Petri disease pathogens in Italian and Spanish nursery, and Botryosphaeria species in Spanish nurseries. So no significant effect was observed against Blackfoot disease incidents. Treating propagation material with hot water at 50 degrees for 30 minutes could be one of the most effective methods to disinfect dormant canes during the propagation process. However, some anecdotal reports of high losses when long-duration hot water treatment is applied to commercial batches of cuttings and root rings have been published. It's important to consider that some Vitis vinifera varieties are more sensitive to hot water treatment than others. For example, in this study carried out in Australia, Pinot Noir was highly sensitive to the treatment, Chardonnay, Riesling, and Merlot moderately sensitive, and Cabernet Sauvignon the least sensitive to hot water treatment. The tolerance of plants to hot water treatment is affected by the climate in which the cuttings are grown. For example, in cooler climate grapevine regions such as New Zealand, it has been shown that hot water treatment at 50 degrees for 45 minutes causes mortality of cuttings. On the other hand, studies conducted in Spain have shown that 53 degrees for 30 minutes significantly improved efficacy against trunk disease pathogens without detrimental effects to cuttings. And finally, hot water treatment is not completely effective against GTD pathogens. In this study, we examined fungal communities after hot water treatment using high-throughput amplicon sequencing in extracted total RNA, and demonstrated that hot water treatment reduced the infection caused by fungal trunk disease pathogens, but was not completely effective in eliminating their growth. Other alternatives could be the use of electrolyzed acid water. This is produced by electrolysis of pure water containing sodium or potassium chloride. This method is characterized by low pH, high oxidation reduction potential, and an increased concentration of free chlorine. So researchers demonstrated that it's effective to reduce Phaeomoniella chlamydospora infections in Italian nurseries. Research has been focused on determining the susceptibility of grapevine rootstocks to Blackfoot and Petri disease pathogens. In general, the incidence and severity of these diseases has been significantly affected by rootstock genotype. However, none of the rootstocks tested have shown complete resistance to Blackfoot and Petri disease pathogens. In 2010, we evaluated the effects of Petri disease pathogens on the grapevine rootstocks most widely planted in Spain under field conditions, and demonstrated that 16149 Cuder rootstock cross of Vitis riparia and Vitis berlandieri was the least affected by the pathogens. However, it's important to mention that this rootstock, the 16149 Cuder, has focused the attention of researchers mainly in France over the last years because this rootstock causes stylosis, physiological problems, and poor behavior in compacted and wet soils. It was called in France as the 16949 Cuder decline with all of these symptoms. Next step in the propagation process is the nursery field, and in this section I will talk about biofumigation. After causing, vines are transported and planted in an open root field nursery. Rooting nursery soil is a critical propagation stage where fungal trunk pathogens, mainly blackfoot fungi, can infect planting material in grapevine. Blackfoot pathogens persist in soil as mycelium in rotten root fragments or as resting spores, called chlamydospores, that can survive for several years. Blackfoot pathogens can also infect alternative hosts, such as wheat or cereals, which makes the implementation of crop rotation in nurseries very difficult. In Portugal and South Africa, researchers demonstrated an increase of Blackfoot disease incidence in a crop rotation cycle. In addition, Blackfoot disease fungi have been detected directly from soil during rotation systems with wheat and barley in Portugal and Spain. Biofumigation could be a sustainable alternative to the use of chemicals. For example, in New Zealand, biofumigation with Indian mustard seed meal reduced Blackfoot disease incidence and fungal inoculum in soil. We recently performed an experiment to evaluate the effectiveness of a native plant species in the Brassicaceae family, as well as a registered biocontrol agent and a mixture of fungicides used to control other soil-borne diseases in Spain to decrease Blackfoot disease infection in grafted plants and grapevine seedlings used as bait plants. In winter, seeds of white mustard were sown at a dose of 1.5 grams per square meter, and then in the spring, when plants reached 50% anthesis, material was chopped up and incorporated into the soil. Plots were covered with black polyethylene plastic sheet. 1 month after covering the rising beds or plots, hot water treated plants that had been treated with either Trichoderma troviride T11 and Trichoderma spirillum T25 or water were planted through the polyethylene sheets into the treated subplots according to the standard nursery practice. Treatments consisted of dipping the roots and the basal part of the plants in Trichoderma species suspensions or water for 24 hours at room temperature before planting. 10 months after planting, once grafted had completed their cycle of vegetative growth and were in a dormant stage, they were carefully dug out of the soil to keep the root system intact and taken back to the laboratory for evaluating natural infections by Blackfoot disease pathogens. Results showed that percentages of infected plants were significantly lower in treatments with white mustard than in the non-soil treatment control and chemical fumigation plots in both fields. So, in our conditions, we recommend biofumigation with white mustard to reduce Blackfoot disease incidence in Spanish soils. In newly established vineyards, it's important to select apparently healthy planting material and also carry out an adequate site preparation and vine management. In this section, I will also talk about biological control as a preventive strategy before planting. Here, some recommendations to select grafted plants. Just to highlight that grafted plants should have at least 3 healthy, undamaged and evenly spaced roots. Grafts should be fully healed, not overgrown, and not able to be broken by moderate pressure applied by the thumb, as you can see in these photos. As I suggested before, mustard seed meal can be incorporated into the soil, or a rotation crop of mustard can be grown until flowering and then incorporated before planting. In addition, compacted soil layers should be broken up before planting, and vines should be well placed in a large planting holes. In many instances, blackfoot disease can be found in association with the condition known as J-rooting. This condition is the result of poor planting of the vines in which roots are oriented upward. Here we can see an infected vine that has developed a second layer of roots due to blackfoot disease in order to compensate for the loss of functional roots farther below. In most of the soil types, even in the deep soils, roots are condensed between 20 and 60 centimeters. Most soil-borne pathogens are living in this portion of soil, so it's important to favor root development in order to avoid the exposure to pathogens, to explore deeper phreatic layers, and to provide greater initial growth. It is also important to select sites with good drainage. Disease incidence will be greater in heavy soils than in medium-light soils and in wet conditions. Regarding the pre-planting strategies, the application of biocontrol or biological control agents could be an option to avoid GTD infections. Over the last 10 years, there has been a frantic search by the GTD research community for microbial antagonists, including fungi, bacterial, and oomycetes. Although some of these studies provided promising findings, the results have not been consistent, observing differences in efficacy depending on the nature of the biocontrol agent, the target pathogen, application method, time of exposure to the BCA, and even the grapevine cultivars and rootstock subjected to study. In addition, most of these studies have been performed so far under in vitro laboratory, greenhouse, or nursery controlled conditions by using rootstock or scion cuttings. I would like to highlight this study carried out by researchers in South Africa under field conditions. They evaluated 8 different trichoderma-based products to nursery vines post-chiosine to control blackfoot disease. Even though trichoderma species were not sufficient to prevent infections by these pathogens, a certain degree of protection was obtained in the basal ends, but not in the roots. We recently performed an experiment to evaluate the preventive effect of 2 potential biocontrol agents, that is Streptomyces sp E1 plus R4 and Pythium oligandrum PO37, and 3 BCA commercial products containing Trichoderma troviride SC1, Trichoderma collingi TK7, and Pseudomonas fluorescens plus Bacillus atrophaeus on blackfoot infection in grafted plants. We used the protocol, the same protocol as explained before in the biofumigation. Dipping the roots and the basal part of the plant in the biocontrol suspensions or water for 24 hours at room temperature before planting. This is the experimental design. We used 2 fields with a total of 960 plants per field. We analyzed 50% of the plants at the end of the first year and the remaining 50% of the plants at the end of the second year of study. Overall, the results show that only Streptomyces was effective in reducing the disease incidence and severity of blackfoot pathogens. However, this effectiveness was dependent on the plant part analyzed. In this case, Streptomyces reduced the incidence and severity only when infection was detected in the basal end of the rootstock. In this sense, in the comparative study mentioned before, these researchers concluded that dipping of basal ends in the Trichoderma dry formulation consistently gave higher colonization percentages than the 1-over soak of bases of vines before planting or Trichoderma field drenching. Further research is needed to evaluate the effectiveness of soaking vines in Trichoderma dry formulations compared to soaking vines for 24 hours in BCA water suspensions before planting. Regarding the management of young vines, growers should avoid placing a heavy fruit load on vines in the early production years. Adequate vine and root development should be allowed to occur prior to placing a heavy fruit load on vines in the early production years in order to avoid stress, thereby reducing the likelihood that endophytic GTD organisms will become pathogenic. In the first year of planting, the focus is on creating a strong and straight trunk as well as formation of roots. In the second and third year, the focus is on incremental cordon establishment. These cordons will bear the crop every year. It is strongly recommended to remove all fruit from the vines during trunk and cordon establishment, since it will compete with root and shoot formation. Thus, during the first growing season, it's important to share the aerial growth among several vine shoots. So don't take just one shoot and start training it. In the first winter, select one vine shoot and prune it to 2 or 3 buds depending on your cultivar or production expectations. In this case, the vine shoot is already on the wire. During the second growing season, the same situation, don't train the vine shoot so quickly. In the second winter, our shoot is already on the wire, but in this case, the vine is already trained. In the third summer, we are ready to train our plant, so growers must also remove the fruit from the vine and avoid this situation. Here we can see clear examples of overcropping 2 years after planting. And finally, in the fourth year, we have our lovely vineyard already trained and ready for getting this yield during harvesting. Well, this would be the ideal situation, sometimes difficult to obtain in many grape growing regions. Just to finish last section of my presentation, I'm going to focus here in pruning, practice and protection. Winter pruning is the main port of entry of GTD pathogens in the vine. A proper pruning practice is imperative to reduce GTD infections. First recommendation is to make all pruning cuts to retain long internodes, the protective bud. In 1-year-old bud, the cut must be made beyond the last retained bud just to leave this protective bud. Growers must avoid making the cut just above the bud. The natural desiccation cone or the trunk disease infection could take this bud. The same situation for 2 or more than 2 years old bud, so don't make the wound in close proximity to the trunk. In this case, it's also essential to leave this protective bud. The second recommendation is to improve the continuity of subflow. Recent research carried out in France highlighted the benefits of the Guyot-Poussard system to ensure vines a healthier and longer life. First, driving the branching development respecting vines' organic growth. The second assumption concerns the continuity of the subflow through the structure of the plant, separating desiccated areas from the main vascular flow. And third, reducing cutting surfaces and respecting the crowns. Cuts must be small on the same side and acted upon 1 or 2 years old wood. A precision pruning greatly reduces the area of wound exposed, thus the risk of grapevine trunk diseases. Next topic I'm going to talk is pruning wound protection. Nowadays we have strong restrictions and difficulties on the use of chemicals to protect pruning wounds. Grafting mastics, paints and pastes are by far the most reliable wound protectants, particularly when they are supplemented with fungicides. These not only provide a physical barrier to stop GTD pathogens spores from entering the wounds, but should be a physical barrier compromised by subflow, rain or cracking when drying. The fungicide can then act on the pathogens. On the fungicides evaluated based on frequency of reports from literature, the methyl-benzimidazole carbamate mode of action group, benomyl, carbendazim and thiophonate methyl, are the most effective against both Botryosphaeria and Eutypa diebac pathogens as well as Esca disease. The methylation inhibitors, the bucronazole and flucilazole, are also very effective against both Botryosphaeria and Eutypa dieback pathogens. Paint and paste treatments are applied by hand with paintbrush or specially designed applicators. This can be very costly, 2 to 4 times the cost of application with a tractor-mounted sprayer, and so prohibitive. Liquid formulation fungicides have been applied with pneumatic sprayers, and more efficient strategies of applying with tractor-driven sprayers have been developed, making it more economically viable for annual post-pruning wound protection in large-scale vineyards. An alternative that is gaining interest over the last year is the use of biological control agents. These restrictions on the use of chemicals have been reflected in the increase on the research done in BCA against GTD pathogens in comparison with chemicals over the last 12 years. Most studies on the use of biological control agents have been focused in the application of Trichoderma species under controlled conditions. In general, biological control agents have shown variable results for preventing infection by GTD pathogens. Although biological alternatives may offer long-term protection, the 1-2 weeks required for biological control agents to colonize the wound creates a window of susceptibility to infection. Here, I show some examples of the good performance of Trichoderma-based products against GTD pathogens under field conditions. More recently, several natural compounds have also shown promise for control of GTD, but further research is required before recommendations can be made for wide-scale application. Now I'm going to talk about a pruning wound protection trial that we recently performed in Galicia, northwestern Spain. For this, we followed the official methods of European countries to evaluate pruning wounds protection products against Eutypa lata. In February, 1-year-old canes of all vines to be treated were spur pruned to 2 or 3 buds, leaving this protective wood and coinciding with the common pruning time in this region of Spain. Wound treatments were applied by hand until runoff within 2 hours after pruning to 3 wounds per vine. On the following day, wounds were inoculated with the fungal trunk pathogens Phaeomoniella chlamydospora and Botryosphaeria at these doses. 2 months after the artificial inoculation, 12 months after artificial inoculation, canes were collected and taken back to the laboratory for disease assessment. We used 5 treatments plus the control. In general, the chemical and biological products assessed were those commercially formulated and currently registered and available in Spain for control of fungal trunk pathogens, except tebuconazole, which is registered to control botrytis and powdery mildew. Pyraclostrobin plus boscalid, Tessior, treatment contains a liquid polymer and it's already formulated to be directly sprayed to pruning wounds without any previous mixing. We use 2 Trichoderma-based products, Trichoderma treviride strain I1237 Skiff and the strain SC1 Vintec. In this column you can see the results of the mean percentage of disease control of each product over 2 seasons. The first column for Phaeomoniella chlamydospora and the second one for Diplodocus areata. The mean percentage of disease control was higher in all cases for these 3 products and ranged from 46 to 60% in the case of Phaeomoniella chlamydospora and from 67 to 82% in the case of Diplodocus areata. Mean percent disease control obtained with the biocontrol agents was low in all cases. To conclude, in this trial, products with a physical barrier provided the greatest percentage disease control, highlighting the products Tessior and Mastic plus tebuconazole, and the Trichoderma-based products showed low efficacy and low percentage of colonization, around 30%. The inconsistencies found in the Trichoderma products' performance in our study and previous reports could be due to different reasons. The first one, environmental conditions such as the temperature at the time of application may have a negative influence in the persistence and implementation of Trichoderma species. The average of the daily mean temperature experienced in the week of the trial setup was around 7 degrees Celsius, a fact that could explain the low colorization obtained by trichoderma-based formulations. Trichoderma species applications after pruning in late winter or early spring would likely provide higher disease control than normal pruning in winter. However, pruning at these moments will surely have an effect in the physiology of the plant. The second reason of this bad performance may be so that short time elapsed between pruning wound protection and GTD fungal inoculation, 24 hours. Previous research reported a greater biocontrol efficacy when artificial GTD pathogen infection was delayed 7 and 14 days after application in Trichoderma species on pruning wounds. These findings suggest that biocontrol agents might need a period to colonize the pruning wound surface and grapevine wood to be effective. And the third reason, so the high disease pressure used in artificial inoculations. The use of pathogen artificial inoculations is very common in the assessment of the efficacy of pruning wound protectants against GTD to guarantee a substantial establishment of infection in untreated inoculated controls for statistical analysis. The efficacy of pruning wound protectants under lower artificial GTD inoculum levels or natural infections in the vineyard should be tested in future studies. In this regard, I would like to present you our European project Vites Qualitas. The main aim of this project is to increase lifespan of vineyards through the identification of good practices of grafting and pruning. Regarding pruning, we are evaluating the efficacy of several pruning wood protectants and under natural infections by GTD fungi in France and Spain. At the end of the project, we will be able to provide a guide for the optimization of pruning practices and protection to reduce fungal and pathogen infections, and a guide to identify and transfer good practices in nurseries and an adequate quality assessment of plants. Timing of pruning may affect the wound susceptibility to GTD pathogens. Environmental conditions and availability of inoculum through the year have been shown to vary among grape growing regions worldwide. It's imperative, therefore, to conduct epidemiological studies on a regional basis in order to optimize pruning to minimize GTD development. In this table you can see the different grapevine trunk disease spore trapping studies showing spore dispersal through the year in grape growing regions of both northern and southern hemispheres. Based on these studies, late pruning, mid-February to early March, has since then been recommended to reduce infections caused by Eutypa lata in California, with weather conditions then favoring a faster healing of pruning wounds than earlier in the season and also correlating with periods of lower amounts of ascospores in the environment. Similarly, later studies conducted in California also showed late pruning as an effective cultural practice to reduce Botryosphaeria diebac pathogens infections. However, late pruning is not feasible in all vineyards. In those vineyards with limited labor force, growers need to begin pruning early in the winter to ensure completion of the activity before bud break. Results obtained in northern Spain on the natural infections of pruning wounds, in particular in Galicia, La Rioja, Navarra and Catalonia regions, show that higher fungal infection abundances occur more frequently in spring than in winter, thus suggesting that pruning wounds could be more susceptible to GTD fungi overall after a late pruning winter. These natural infection trials must be complemented with spore trapping studies on these regions in order to optimize pruning to minimize GTD development and make recommendations to growers. In this sense, these researchers in Spain recently developed a model to predict disease risk caused by Phaeomoniella clavidospora in vineyards, the main causal agent of Esca disease, and estimated that these pathogen dynamics were best explained when time was expressed as hydrothermal time, accounting for the effects of both temperature and rain. The equation obtained in this study should be validated with independent data collected in different years, location, and viticultural systems. Once the equation developed here is validated, it should be incorporated into a decision support system that will help growers to adopt effective practices for controlling GTD. Remedial surgery, where visibly infected parts of the vine, cordons and or trunks, are cut and removed, has long been implemented in vineyards, mainly in Australia, to control Eutypa dieback. The success of remedial surgery is dependent on the removal of all infected wood, including removal of an extra 10 to 20 centimeters of apparently healthy tissue beyond any visible staining. However, the success of remedial surgery is very limited if infection has reached the ground or graft union. In this case, grower was way too late for renewal. We see Eutypa dieback symptoms even if the origin of the water shoot was the lower part of the trunk. This is also particularly true for Esca diseased plants, where internal necrosis is often observed in both scion and rootstock wood of affected plants. Thus, completely removing infected wood is very difficult. To conclude my presentation, I would like to recommend reading these papers, the first one by Helen Waite and collaborators about grapevine propagation, principles and methods for the production of high-quality grapevine planting material. The second one, a review we published in Plant Disease a couple of years ago about the management of grapevine trunk diseases in nurseries, young and mature vineyards. So hope you enjoyed the seminar and thanks for listening.